atoms that, according to the very meaning of the word, have no parts at all. But on the other hand, some philosophers maintained that our universe is not atomistic, but Junky. Junky Junky is a word, I think, coined by David Lewis. David Lewis to be considered as the greatest metaphysician of 20th century. And Junky means there are no atoms. We can go down ad infinitum. We have a certain object and we can find an object that is smaller and another new object that is smaller than the smaller, and it never ends. The universe, so to speak, has no bottom level at all. It becomes smaller and smaller. And the question is, Peter Simons maintained that this was one of the great question of Mereology, whether our universe is Junky or atomistic. If we consider, so you might think the universe has a structure of such a power set. The power set, the atoms are the smallest one, and what exists in the world are just sets of these atoms. So Px is a Boolean algebra that offers us an atomistic model of the universe. A Boolean atomistic model. The problem then is, do we have models, Mereological or topological models that offer us non-atomistic models? And this is indeed the case for regular open subsets of Euclidean space. So the regular open subsets are of form a Mereological system without atoms, a Junky system. So let's now explain this in elementary terms. Yeah, here we have an object, an open set of, say, Euclidean plane. Why this is Junky? What does it mean that it is Junky? According to the regular open model of the universe, the only thing that the only objects that exist are regular open regions. There are no points. They are just open, regular open regions. And this system is Junky because we can always find a smaller one, and it never ends. Why does it never end?
It has no atoms and it can be divided ad infinitum.
Yeah, right, but if you look at this geometrical model, it ends up, so to speak, in a point, but points
But you
are
can
not.
still divide it. You can still divide the point because it's got
No, the point. You cannot divide it. You don't reach the point. You reach the point from the ordinary perspective, because the point is not interior open, not interior closed. And in this universe, the only things that exist are elements of, are sets of that are regular open. Little exercise why a point is not interior closed. What?
Perhaps a comment, a more philosophical comment. It seems to me quite strange. I think that the majority of physicists and perhaps some philosophers would disagree that the real line with points is atomistic. I mean, there's this strong kind of intuition that an atom has to be something that has some sort of like non-zero dimension. So actually, I mean, I think that most physicists would say that this is like what we mean by Junky. That we can actually divide everything that has some sort of like, you know, dimension and can be divided ad infinitum. But points are kind of like, you know, sort of like this abstract sort of thing.
But when you take the regular open subsets of the real line, it's like that. This is what you say exactly. You can't reach the points.
Yeah. But my point is actually that from an intuitive point of view, like points are not considered like, this is what like,
yeah, exactly. If you take the structure like regular algebra of the grid line, there are no points in there. It is non-atomistic.
Yeah, but okay, let's forget about this concept of regular open sets. Let's just talk about ordinary, speak about ordinary, real line, ordinary. Like, if we consider like two possible sort of theories describing, let's say, physical space-time. So, I mean, some people say, okay, physical space-time is sort of is discrete. Some people say it's continuous. So I would say like, my intuition is that when we talk about an atomistic conception of space and time or matter, what we don't mean that you can distinguish points. I mean, this is something people can like take for granted. I mean, people who are not perhaps trained in topology, they take for granted that points are there. But we are interested in some like, well, or maybe actually to put it in the other way around. I mean, actually, what people mean by I mean, like intuitively, when they talk about an atomistic conception, like actually they say that in an atomistic conception there are no points. There are just you know, those like tiny kind of like, I don't know, elementary particles, and you cannot go any further. There are no points. So it's like there's a kind of like a clash of intuition. That's all I wanted just to say. That there may be some sort of like clash of sort of philosophical intuitions here underlying. I know.
I mean, I start with, so to speak, an old-fashioned Euclidean conception of point. A point is what has no parts. So it's an ultimate part. There may be other, point may be part of something, but the point itself has no proper parts. They are little, that's all. And what I want to show is that in this account of the world consists of regular open regions, there are no points, because the point that we seemingly reach here does not belong to the regular open ones. And Mike, wait a moment, and I'd like to that everybody understands why this is the case. Why such a Euclidean point in Euclidean space, in standard account of Euclidean geometry, does not belong to the set of regular open ones. This can be answered by everybody here, by the knowledge that he or she got yesterday. What is this An interior region, an interior closed region, an open and regular open set. We should have this one. Why we don't have. So please calculate, everybody should calculate, be able to calculate what is this? The interior closure of a singleton, that is to say of a set that only consists of one element. So what's a closure of a point? In Euclidean topology, the point itself. So what is still missing? What's the interior of a point? According to the very definition we learned yesterday. It's empty. So there is no such smallest element in this model of the universe. That is to say, R or X offers us a model, rather elementary model of a universe that is non-atomistic, that is Junky. And this is important because the standard Boolean Mereology only offers us a pointy universe. That's all I wanted to say. So here we have an ontological application that shows us that at least there is the possibility, the conceptual possibility of a Junky universe. And as far as I know, these regular open subsets are the only example at hand. So here our enriched topological language gives us some new philosophical intuition that we can't reach with sticking to the ordinary set theoretical language.
I just wanted to add that, so I agree with that, of course. We have two notions of point, right? One is metric, no extension, and the other is, let's say, compositional or mereological, no proper parts. And of course, the two don't necessarily go together. Here we don't have the metric, so the notion is purely mereological or compositional. But of course, when it comes to physics, but also some sorts of metaphysics, you may want to say that there are points in the mereological sense, i.e. atoms, which however have some extension. And the question of whether or not there are extended atoms is an interesting question. And the answer is yes, if and only if the two notions fall apart. But the metric notion and is not the one that's being discussed here. This is purely mereological and therefore topological in terms of interiors.
Well, I absolutely, if I may just make a comment, I absolutely agree with that, but my point was, of course, I agree with all these formal results. They're unquestionable, but philosophical, because the point that you're trying to stress here is that this theory has an important philosophical application. And my sort of objection is that there's one particular philosophical meaning of atomness and atomless, and that actually is not captured by this theory, which is precisely the meaning that the sense yes, that was presented. Basically, many working physicists and philosophers, what they mean by the physical space being containing atoms is they simply ask the question whether there are some minute elements of space or time which actually nevertheless have certain dimension. So actually they wouldn't be happy with your way of kind of explaining the intuition of what it means to be an atom in terms of simply being a part. No, they want more. They want to have a part which actually has a dimension, which actually
Yeah,
is not zero dimension, it's not a point. So this is basically all
Okay,
I want
I
to-
agree. Well, one may say from a quantum perspective, there are the smallest, the smallest entities somehow defined by Planck's
Yeah, something like that.
minimal, but
Some scale that you can go any further, any sort of, yeah.
but this would be the next step, so to say. I'm starting with the most primitive one, namely the Euclidean pseudo definition of what is a point. A point has no parts, and the only thing I claim that topology offers a model how this can be explained, but in a model that that is the Junky in this sense, smaller and smaller and smaller. You may deny that this is the case in physics, but for the time being, we are just talking about mathematical or conceptual possibilities.
Yeah, absolutely.
And it goes beyond the standard knowledge of Px as the only policies. Okay. So, now it's my time. What I want to say at the end,
Sorry.
What I'm preaching is, that closure operators are important, and that closure operators offer a rich, or need a rich theory of combinations of various operators. And topology is not the only one. There are many other rivals of theories of closure operators that all make their contribution to theory of space. Topology is not alone, so to speak. Theory of convexity, theories of similarity, and other more modern accounts should be taken into account. So, in the end, I like to discuss here a list of closure operators and their applications in modality, in philosophy of science. The most primitive one is Boolean algebra of subsets of X. This has applications in model theory, namely the closure operator is interpreted as possibility. This is an account presented long ago by Tusky and McKinsey. So, here you have a set of possible worlds, and the concept or predicate is expressed by a subset of possible worlds for which it holds, and then the closure operator corresponds to the Mereologic diamond, and usually this is the box corresponding to necessarily X. And topology offers a well-behaved, very standard system of modal logic in this sense. Another possibility of applying topological operator is this is a Heyting algebra. The open sets are Heyting algebra. They correspond to intuitionistic logic. Correspondingly, we have the co-Heyting algebra of closed sets, also mentioned yesterday. This amounts to the logic of contradiction offered by Priestley. Yeah, I just mentioned the regular open ones, and also interesting are the so-called Clopens and the Boolean algebra of Clopen sets. A set is Clopen if it is open and closed, and a great result of Marshall Stone showed that the role of that any Boolean algebra can be represented by a Boolean algebra of Clopen sets of some space. So Stone showed here that there's a direct correspondence between Boolean algebras on the one side and certain topological spaces today called Stone spaces on the other side. And this is very well behaved. One may show that the correspondence is correspondence between the category of Boolean algebras and the category of Stone spaces. And also interesting maybe the Boolean algebra of Borel sets that we use in measure theory. Measure theory is a theory of measuring length or measuring volume or measuring areas, something like this. Okay, this is the first part of my talk, namely topological operators, or one may say topology via operators. This is a natural consequence of what we learned yesterday, starting with closure operators, interior operators, and was elaborated, one may say, by the Polish school of mathematics, one of whose leaders was Kuratowski in the 1930s, 1940s. If someone wants to read this in the original, Kuratowski, together with his collaborator Mostovsky, wrote a series of lecture books that are still in print, and I really recommend these books. You will find there things that you do not find in any other textbook of topology. So it's time for a break, or?
Yeah, it was good. Thank you very much.